Hello, good morning and good afternoon, everyone. Thank you so much for joining us. I'm delighted to be presenting this webinar on behalf of Acronix today with Acronix partner Myrtle.ai. I'll be your moderator today. I'm Sally Ward-Foxton with EE Times. I'm joined by Bill Jenkins with Acronix and Julian Mack with Myrtle.ai. Perhaps I could ask you both to do a quick introduction first, if you don't mind. Maybe Bill, you could go first.
Sure. So again, Bill Jenkins. I'm the Director of AI Product Marketing at Acronix. You know, Acronix might be new to many of you, but it's the other or the third FPGA company out there. We're a lot smaller company, but we're the only one that has the eFPGA and the FPGA. So that's us.
Thank you. Julian, maybe you could introduce yourself and tell us a little about Myrtle.ai.
Yeah, sure thing. I'm Julian. I'm a machine learning researcher. So I train deep learning models day to day. And Myrtle, the company I work for, we accelerate deep learning workloads at inference time, and particularly when the low latency responses are required. So that's what we do. We work across a range of applications. So it might be financial time series processing or computer vision or the conversational AI applications that we're talking about today. But yeah, looking forward to getting into it.
Great, thank you. So we're going to be talking about a new automated speech recognition or ASR solution that Myrtle.ai and Acronix have developed together. So this is Myrtle.ai's hardware accelerator IP on an Acronix Speedster FPGA. We're going to tell you a little bit more about this solution in detail. If you're watching us live on LinkedIn today, if you have questions as you're watching our chat, please feel free to type them into the comments box. The LinkedIn comments box should be below this video. We'll answer all your questions at the end. We'll have a Q&A session where we'll get to all your questions, as many as we can in the time that we've got. Okay, first, maybe we can ask Bill to kick us off. Bill, perhaps you could set the scene and just tell us a little bit about the landscape for conversational AI systems today.
Yeah, sure. So conversational AI, for those who aren't familiar, it's interacting with a computer as if it was a human. So the idea is that you need it to be as real time as possible so that the conversation is fluid and transparent, that that's not a machine. We've all called a customer service number and gotten the very long pauses, or it only knows certain words. That's kind of the direction we're heading away from, to try to get it into actually more conversational interactions. So you can imagine the different types of markets would be call centers is a great one, customer service and call centers, but then a lot of transcription services, so medical, financial, even public safety. When officers take off their camera at the end of the day, they transcribe all that video. And virtual assistants is probably the most common area where everybody talks to their phone, they talk to their Amazon Alexas or Google Homes. But basically, there are three components that make up conversational AI. The first one is ASR, right? The speech to text portion. The second piece is kind of the natural language processing. Also now becoming more and more prevalent and prominent is generative AI. Another thing that we're looking at accelerating with Myrtle. And then the final piece is text to speech, which is converting that output text back to speech so that it synthesizes the human voice. Those are really the three main things that make it up.
Cool. So the solution that you developed with Myrtle.ai, this is a real-time streaming speech-to-text system. Tell us a little bit about that, please.
Sure. So that solution, I guess we'd call it an appliance. It's a real-time streaming solution for ASR. That's legitimately what it is. It's for real-time. I need fast real-time streams, as many as I can get. But it's basically a server, 1U, 2U, 4U, however big the server needs to be. You can fit up, most servers I think we're looking at right now, 4U with 8 cards in them, kind of sizes. But it's basically that hardware, one of our vector path cards plugged into that server with the Myrtle software stack running on it. And that software stack obviously runs both on the CPU and the FPGA, the acceleration IP running on the FPGA. But they also provide the English language support out of the box, but the ability to retrain the models with your own data set or different languages, whatever, using your standard PyTorch. And then what we're trying to do is abstract away the FPGA, because so many people might be familiar with the benefits of FPGA, But they also know some of the drawbacks, which is it's difficult to program. So what Myrtle is able to do is provide a very simple WebSocket API interface that abstracts away the fact that there's an FPGA in the system. And the result is we're getting, about 1,000 real-time streams today in 54 milliseconds of end-to-end latency. And we'll talk about this a little more later, I'm sure. But the idea of that is that we could probably do up to 4,000 streams, but most people want that word error rate, that better accuracy. So even 1,000 is so much better than what people can do today. That it's a good sweet spot, 1,000 to 2,000 streams. And then actually. Sorry. I was going to say if Alex, if you could throw up that picture, the slide, this might be pretty helpful too for people to kind of get a feeling for, what we're doing here with this solution. So real-time speech comes in through WebSocket API, gets fed into the CPU, which does some pre-processing, passes it over to the inference server, and the inference server really is just moving the data over to the FPGA. And the good thing is we minimize that back and forth to the CPU transactions here by, letting the FPGA do the complex stuff, the mathematical operations, and typically encoder and decoder type things, and passes the resulting text back up to the CPU, which then sends it out as a transcribed, WebSocket API. So
sorry to jump in there, Bill. And if you're not familiar with a WebSocket API, it really is just like if you're familiar with sending HTTP requests over GET and PUT requests, which I guess a lot of engineers will be familiar with here. It's exactly like that, except that it's a stateful connection. So the server and the client need to know that they can continue talking to each other in order to get this really low latency back and forth. Yeah, back to you, Bill.
Great, thank you.
Yeah, and we can actually show, maybe it makes sense we can actually show you a demo of this solution working. So if, Alex, if you want to throw that demo up. So this is basically just, we call it the AVL, the Acronix Virtual Lab. And what that lab does is it's a data center that hosts our servers with the cards, and this solution is running on them. And you can remote in and get access to it. But what it's basically showing you is, in this case, we're showing 1,050 streams. What you can't hear in this demo, but if you were to actually do it yourself and play it, when you click on any one of those 1,050 boxes that are there, you can actually listen to the words being spoken and then see the transcription in real time as it happens. But it's doing it with 1,050 streams. And then there's a couple of different charts and stuff that show on the right where you can kind of look at your latency and especially the 99th percentile latency, which is basically for us typically under 55 milliseconds.
Perfect, thank you.
Sure.
It sounds like you've optimized for word error rate versus the number of streams, and you've optimized on about 1,000 streams. What kind of application needs 1,000 streams concurrently? What kind of situation have you optimized for?
So you can imagine certainly call centers and customer service. Those guys get 50,000 plus calls a day, typically lasting over 5 minutes a call. So just being able to do that with a couple of cards, right? Comparatively to the thousands of cards it would take with the alternative solutions. That's certainly one area where there'd be a huge benefit, but things where you need, even if you said like every hospital, every police station, where you have hundreds of streams coming in, voice recordings of phone calls, there's plenty of opportunity in those various markets I mentioned earlier to leverage this, and hopefully some new ones that will spawn as this gets better.
Cool. Yeah, and I guess just to add to that, ASR providers who are already doing the collation of many users, and they're the people that are really going to benefit from the TCO savings that we're offering here.
So what kind of system might somebody already be using for this task, Bill? I saw in the press release, you say you can replace 20 CPU servers or 15 GPU cards. Like, what kind of CPUs are you replacing? What kind of GPUs are you replacing here? What are you measuring against, and with what performance metrics? Yeah,
so that claim is made based on our performance, the number of real-time streams that we can do. So since we can do 1,000 real-time streams today, that's with very competitive word error rate. When you look at that performance of a CPU or a GPU, since we're doing much more with less, especially for real-time streaming, we're basically replacing your typical GPU or CPU, which CPU can do 8 to 10 real-time streams. and we're doing 1,000. And GPUs can do dozens, maybe hundreds, but certainly not the scale that we're doing here and the latency we're doing. And also the GPUs don't. We're using an RNNT, an RNN transducer model. Myrtle is in the FPGA, so that's not something GPUs do really well. They tend to do transformer models, so the performance of this smaller model tends to be more suited for these streaming applications, where the transformer being significantly larger is going to add much more latency. And so when you look at the kind of CapEx and OpEx, it's at scale, it becomes a millions of dollars kind of savings, especially if you need the kind of volume that multiple cards would bring in comparatively to using a cloud or a CPU GPU solution.
Yeah. I think you said 54 milliseconds on the latency. How are FPGAs so good at low latency, or how are we so good at doing real-time AI processing with FPGAs, and how does this compare to what you might get from a GPU, for example?
Yeah, so I mean, if you think of a GPU is a warp-locked architecture, which means that it'll execute a certain number of single instruction, multiple thread on that architecture at one time, but it basically will, to compensate for the fact that it has all these warps that have to run on the core, it'll break the data up and then pass it over, but it's always doing one instruction across a lot of data. So it tends to batch up that data, which of course adds latency. And then it has to go back and forth to memory, back and forth to the CPU. But an FPGA, and why an FPGA is so good at this, and specifically even why Acronix FPGAs are good at this, is FPGAs are good at latency because, and if you think about AI as a whole, the models tend to look like graphs, and FPGA designers turn graphs into pipelines and arrays very efficiently. Actually, Alex, if you throw up that third chart, and so what happens, and where we're different, is that architecture, we can actually run multiple functions, multiple threads simultaneously. So in this example, I'm showing 9 simultaneous functions running on the FPGA, and maybe they're passing data from one to the next. So it doesn't always have to go to external memory. It doesn't always have to go back to the host. You're keeping the data on the device. Ideally, maybe you're going to memory. We happen to have GDDR6 memory with over 4 terabits of bandwidth. So you get a lot of external memory bandwidth, as well as internal memory bandwidth in the FPGA fabric. So this really is conducive for a low latency application, because you're keeping the data, you're using the results from the previous compute in the next compute without needing to leave the device. And that really is what drives that latency. And one other thing I'll mention, and maybe we'll talk about it later too, is our device has a NoC, a 2-dimensional NoC, a network on chip that really makes it easy to solve the data ingress egress problem of getting data in the FPGA and through the FPGA.
Yeah, I think shifting data around is a very important part of most AI applications, right? So I was wondering, what about at the system level? How do you move data kind of between the CPU and the FPGA kind of quickly and efficiently?
Yeah, so I think, well, I'll kind of reiterate some of the stuff I just said. The NoC is a great way to do it, because there's kind of 2 NoCs. There's one that does the I/O. So I can come in through PCI Express and go right into GDDR6 memory, then come out of GDDR6 memory into the fabric, get processed, back out over Ethernet or something. And that's all done with a 2 gigahertz, 20 terabit per second bus, multiple buses throughout the FPGA. And on top of the I/O, there's also a fabric NoC. So we can get in and out of the fabric from the peripherals seamlessly. And all of that takes no FPGA logic. For FPGA designers, they're very familiar with all the logic required to connect to an interface. We eliminate all that, because the NoC is basically just an AXI address point that gets dropped into the logic gets dropped into through a network access point, and then it gets access to it. And the other thing is, again, like with the MLPs, we call them machine learning processors. Think DSPs and other architectures, but it does the multiply accumulate, and Julian will definitely talk more about this later. But it has 72 kilobits of block RAM associated to it, so you're able to do that result reuse. But ultimately, the goal is, by doing all that, you minimize the need to go back and forth to the host.
Yeah, I got it. I think it's time to let Julian speak. Julian, tell us about how Myrtle.ai fits into this project, and how are you working with Acronix on this?
Yeah, right. So, I mean, as Bill says, we abstract away the FPGA for your normal machine learning researcher like me, actually, understanding how to program a FPGA is a whole load of gory details that I don't really want to deal with. And so Myrtle, people sitting next to me in the other room, they program it, and we have a whole lot of experience and IP to make sure that our designs are getting the absolute most out of the underlying hardware. And yes, as I say, some of that is our IP, some of that is just experience of how to build these systems. And then we hide it all behind behind a nice WebSocket API so that the user can interact with it as though it's just a web server on a remote machine. Yeah, so that's what we're doing in this. That's our offering to this piece. I don't know if we've lost Sally there.
Oh, no.
Oh, sorry, I think I lost you guys. I hope it's not going to be, I hope the internet connection is not going to be a problem. And thank you, Julian. I note the system that you've designed with Acronix is supporting 1,000 concurrent audio streams. What's the difference from your perspective between processing the audio offline and streaming it for an ASR application?
Oh, yeah, I mean, a massive difference. So I guess it comes down to whether you allow your model to listen to the whole sequence before it then starts transcribing, or whether in the streaming case you say, okay, no, you have to predict what you've just heard as soon as you hear it. And that's what the streaming case is. And it means that the models that you're able to use are a bit different. And it definitely means that the context that those models see are very different to the offline case. And I guess one more thing that's just very different between the offline and the streaming case is, Bill, I think, touched on this, is you're saying that you can batch up data. You do that in the offline case. And for example, if anyone here has trained these networks, you'll be training on GPU, most likely, and you probably need to run at batch size 128 in order to get the maximal efficiency from the expensive hardware that you have. In our case, if you're doing low latency streaming, you can't wait for 127 other elements in the batch. And I say that maybe with an asterisk because it depends on the input distribution of all of your requests, but because of this streaming, the thing that Bill showed, this graph with the data flow, that natively supports streaming. That is, function 1 is computing, well, function 2 is computing the second sample, while function 1 is computing the one after that. So you've got the data flowing in and computation happening in this streaming fashion natively.
Yeah. So Julian, I understand Myrtle.ai works a lot with FPGAs, or almost solely with FPGA hardware. From your perspective, why are FPGAs so good for AI acceleration?
Yeah, I'd say solely, really.
Yeah,
that's what we do. We partner with various vendors, but we're focused on getting high performance from these chips because we believe that they're great in these particular workloads that Bill discussed. I guess I mean, Bill covered a load of this. It is about the data transfer. The data needs to be where it's needed at the time that the computation happens, and the more trips you have back and forward to external memory, the larger the latency is going to be. If you need to wait for it for batching, the larger the latency is going to be. But I think Bill's covered a whole load of that, so I won't go back through that.
Yeah, it sounds like you have optimized for RNNT as well for that type of network, which I think GPUs find difficult. That's another key thing for FPGAs is this adaptability or flexibility, right?
Absolutely, yeah. So the fact that, and I guess that this also goes to the model development because these models change frequently, and we change the models that we're supporting, and so we can do that on a software timescale rather than a hardware timescale, which is great. and necessary for these types of workloads. And I guess most people will be familiar with what I'm referring to there, but that's in contrast to taping out an ASIC, which is the alternative if you want these kinds of performances.
Come back in 2 years. Yeah.
Yeah, exactly.
Exactly.
Exactly. When the whole world has moved on. Yeah.
Exactly. We've invented something new by then. So you've got a neat trick with precision as well. Tell us a bit about this.
Right. Yes. Well, this is not Myrtle's trick. This is a development in, I guess, machine learning number formats over the last few years. So we're using something called block float 16, which is natively supported on the Speedster, and that is it's, despite its name, it's basically an 8-bit number, and so what we're maybe I should take a step back here. The reason you would want as few bits as possible when you're inferring these workloads is because you win twice. So you win when you transfer the data, the weights from memory, and bandwidth is often going to be the thing that you're bottlenecked on, particularly in the low latency setting. So you win just from the compression of making your 32-bit number an 8-bit number. But then you can also win again, potentially, if you support these lower precision formats, the multiply accumulate operations that you want to do with them that make up the backbone of these neural network models. If you support those in hardware, which, as I say, these are this block float 16 is supported on the Speedster, then you also get the compute time savings. So you want it for both of those reasons. And yeah, to then go in, I guess, to what is block float? It's the combination of two breakthroughs from Google and Microsoft over the last 5-6 years. So these models are, well, once you've trained a model, you'll have a 32-bit, what's called full precision model weights. And what Google realized is that you don't actually need all of the significant figures in that number. You really just need the range. That's what, and specifically, you need the range in order to get the same accuracy, the same quality. So you can basically just double your throughput by halving the number of bits available to the significant figures. So that's great. That's widely supported. That's supported in TPUs and GPUs and FPGAs. And then Microsoft came along with a second insight, which is built on the first, which is that you really don't need to have an individual exponent for every number, because you can share the exponent across 8 or 16 numbers that are adjacent in the weight or the activation matrices. And that is based on the intuition that the weights of a neural network, for example, they all start and stay in a very small range of numbers. And even more so, within a particular layer in that network, the range is going to be even smaller. So you don't lose basically any accuracy by performing this. And you're ending up with effectively 8 bits, because that's how many are left in the significant figures and the sign per number, plus a little bit of exponent that you've shared across a load of numbers. So yeah, that's how we store the weights, and some of the calculations that we do in this product take place at Blockfloat as well.
So Blockfloat 16 sounds very cool. It sounds like a bit of a cheat. Is there any particular synergy between Blockfloat 16 and the ASR application in particular, or are we going to start to see Blockfloat 16 coming in for other AI applications as well?
Well, yeah. So it's widely applicable, and it's hard to use on a GPU because it's not natively supported. But Microsoft are using this and have been for a lot of years in their data centers for their production AI workloads. I guess just from my side, as a machine learning person, the flow is much easier with this type of quantization because you don't need to do anything special at training time. You just take an FP32 model and then you quantize it after the fact. So that's a massive benefit versus maybe 3 or 4 years ago, everyone was using also 8-bit numbers, but they'd use int8. That is still used, but the benefit that requires quite extensive changes typically during training, at least to get all types of models at the same quality that they were at FP32.
Yeah.
Sorry, and to your question, I've talked around it, but I didn't answer it. There are a few FPGAs that support this, the compute for this, including the Speedster. So not only are you winning on the bandwidth side, you're also doing the compute at this precision. And I guess because they're flexible, that's what enables it.
That's part of it. Yeah. Maybe this is a question for Bill, is what is required on the hardware side to support these interesting new number formats? Block float 16 is quite an interesting one, but tell me about what's required to support different precisions from your perspective.
Well, so in theory, the FPGA can support any precision.
Okay.
Because you can build logic out of the fabric, the FPGA fabric, binary, ternary, whatever you need it to be. You can concatenate into try to utilize the register space much better. So technically you can do anything, but of course the trade-off is performance, right? The more I get out of the dedicated hardware blocks, like the machine learning processors, the performance hit, you're not going to be able to run quite as fast with this throughput. But basically it's our machine learning processor blocks that support the different precisions. So there's an integer multiply accumulate block, there's a floating point multiply accumulating block, and there's obviously different precisions built into that. And so if we start seeing trends, like we could do FP4 in that machine learning block, if we see that trend into even binary and ternary networks, it wouldn't, next version of the chip might have, another mode in it or something, right? We'll add we'll modify the hardware to kind of tailor ourselves to the what looks like it's going to be the norm.
Got it. Thank you. Julian, how directly responsible is the block float format for the performance figures we talked about earlier? I guess we can reduce precision, get more throughput, use less compute. How big a part of the secret sauce is the number format?
I guess it's a very important part, but it's certainly not the only thing. Okay. So Myrtle AI has this compute block called the MAU, and this is our IP that we use across all these various applications. And that is our way of programming these chips and doing the thing that Bill described of you're effectively mapping the layers of your network to locations on the chip. So over quite a lot of time, we've got that block very performant. And I guess maybe coming back to the GPU comparison, the ability to get make efficient use of the MLPs is really what stands us apart at the low latency cases. So if you're only getting 15% utilization, then that's kind of explains almost the 10x of TCO cost. If you're locally, if you've got a layer that's fully utilized on the chip, you're getting almost 100% of the theoretical throughput, the theoretical tops, which you're not really able to do in the GPU paradigm.
Yeah. So Julian, it's Myrtle's trained model with Myrtle's tailored hardware accelerator IP. To what extent can we customize the solution that you're providing?
Yes, so the models that we provide are English language, and they should be pretty good in the general case. What we find, though, is that the people that have workloads of this size, I mean, if if you have 1,000 real-time streams you need to service, you're pretty a long way down your ASR journey. And so typically, well, for the customers that we're the lead adopters that we're speaking to at the moment, they have chosen to retrain the model on their own data to specialize it for example, particular verticals. So it might be for the call center. And the more specialized you go, the higher, well, the lower your whatever rate is going to be in that particular segment. And there's always a trade-off there. The more specialized you go, the less good you are in the general case. So yeah, we think our general models are pretty good, but we expect the majority, perhaps not all, of our users to take this retraining path, which I'm happy to describe if that's of interest.
Yeah. Please, could you tell us a little more about the retraining path?
Yeah, sure. Yeah, well, so we have a repo that we make available to customers and potential customers. And what the user of that will need to do is take their training data, put it into the format that the repo expects, and then set aside some GPU compute, and then run the training with the defaults that we think are correct for their case. So we're not in that loop in the sense that, and this is quite important, I think, to a lot of customers, we don't touch anyone's data because that's theirs. Yeah. Of many of these companies is built on, right? Yeah. So yeah, we're not in that loop, and we also don't touch the weights. I mean, they're on the chip in the design, but Myrtle never has possession of our users' weights either, because I guess a way to think of the weights is it's the distilled data. So yeah, we're out of the loop on that. And if someone has a particular format also that their data is in to start with, speak to us and we can potentially support that if it's a general one and it's not just your in-house format.
Okay.
Yeah.
Okay. So maybe if people are listening to this, Bill, maybe someone's listening and they're an ML engineer thinking, oh, this sounds great, but they're not an FPGA expert, or maybe people have even less experience than that. How easy is it going to be to get this up and running if you've no FPGA experience, or maybe even no ML experience? Is it straightforward?
Yeah, I think so. And I think that's due to what Myrtle, that software layer that they've built, that WebSocket API, it really abstracts away the FPGA. So you really don't need to know anything about the FPGA. They've done the hard part by putting the workload in the FPGA and then giving you a simple interface to it. We're actually working with another partner who's kind of adding a layer above that. So if you're in a cloud environment and you're, it'll extract the audio and create a WebSocket API and then load balance across multiple cards and manage that one level higher. So that's the key point of this, right? Is we don't want you to be an FPGA designer, and the more towards software and machine learning you are, the less you're going to care about the hardware. So what I want people to remember is it's simple to use because you're just writing software to interface to a WebSocket API, and we're going to give you the performance both in word error rate and throughput, parallel real-time streams that should, based on our early engagements with our customers, which should be very appealing and something you can achieve otherwise.
You certainly make it sound very easy. Maybe even I could do it. Thank you so much, Bill. Thank you, Julian, for all the details on the new ASR solution. We now have some time for Q&A. If you're watching us live on LinkedIn today and you have a question for Bill or for Julian, please go ahead and type it into the LinkedIn comment box, and we'll answer as many as we can in the next 15 minutes or so. Okay, I see we already have a question here from somebody watching us on LinkedIn. And they're saying, mostly it's an inferencing engine. How are you doing the training in real time, and what is training hardware?
Okay, that sounds like one for me.
Yep.
So we're not actually training in real time. So the training all happens ahead of time offline, and you can you could do it however you want. You're probably going to do it on a GPU. That's the de facto standard for all training workloads. So it's specifically in the inference case that the FPGAs are going to be competitive. So having done that training, the flow is to run some Python scripts to compile that checkpoint that you get at training time down to something that runs on what we call the MAU, the compute engine that I was talking about earlier. And then if you're interested in the details, you then run a Docker container to start the server, and then you can send requests to it. So it really is as simple as that. I hope that answers your question.
Okay. Another question from the audience. Who's the competition for this technology?
Well, I would say the number one. I'll take this one. The number one competition is going to be, I think, the cloud service providers, like Google and Amazon tend to provide ASR as a service or that functionality. And there are certainly people who store their data up on the cloud, so the data is already there. And again, as I mentioned earlier, we have a partner we're working with, and ours today is running in a data center. We can backhaul to Amazon or Google or AWS or Azure. We can use, so people can continue to use their front end that they're used to, but then it runs on our hardware in the back end. So the reason people would want to do that is cost savings, right? Your significant cost savings in time and effort. There are other competitors who do enterprise solutions on-prem, but typically they're not going to get this kind of performance. I think most everybody who needs this level of performance goes to the cloud, and the people who are doing it with enterprise on a CPU, maybe they're even using a GPU. They're probably not the scale that we're going after, where you need hundreds or thousands of streams.
Got it. Thank you. Okay, a question from Edward Sanchez, watching us live on LinkedIn. Is any of the RTL for running models on Acronix chips open to the public for experimentation?
Well, I can tell you that the stuff that Myrtle is doing is definitely not available for public consumption. And I would say that, we're, as I said in the beginning, we're a small company, so we don't have a ton of libraries and stuff that's open source for people to play with, design examples and reference designs. So I would say the answer to that is probably not for Acronix specifically, because everybody that we know who's done this, whether they're doing CNNs or generative AI or ASR type, RNNTs, they want to keep that proprietary. The effort to optimize that RTL being so challenging, they don't necessarily want to release that. And, we haven't necessarily built design examples or reference designs to show you how to do AI specific things. Certainly mathematical functions and DSP-like functions we can show you, but RTL to do AI to the public isn't available really today.
No, and what we haven't done this yet, but we are likely to open source the training repo that I mentioned. So we want it as much as possible to be open so that people can try it and get as far as they can get without speaking to us. If they don't want to speak to us, although please do come and speak to us. But yeah, the RTL is not going to be in public anytime soon.
Thank you, both of you. Okay, we have another question coming in here from our LinkedIn Live audience, from Andrew E. Wilson. Does Acronix have an affordable dev board or cloud service for early development?
Affordable is such a subjective word.
Right.
Yeah, I think it's great. It's certainly cheaper than GPU cards. So we have a vector path card that we sell today. That's kind of your PCI Express plug-in card and it's meant to do these kinds of workloads. A lot of memory, get you in and out of the FPGA through Ethernet and PCI Express. I forget. I think the MSRP on that is around $8,000. Of course, it's volume-based pricing, so if you're buying a lot, the price can go down. And then for cloud service, I kind of talked about that earlier before. We have our AVL, so the AVL, the virtual lab that hosts servers in a data center that's running this demo that we just showed. We can provide people access to that if they want to play with the demo. If they actually want to play with it, then we're working with that partner of ours to create, the cloud version of our backend in the data center. So if you're using AWS or Google or Azure or whatever, you could use that as a front end and try with ours. That's still being developed today. We haven't quite rolled that out yet. We're still going through. It's probably a few months away from being finished and tested and available for everybody. But if you are interested in playing with it, that's certainly a conversation we can talk about, even getting you access to the AVL to play.
Great, thank you very much. Okay, any more questions from the audience? Otherwise, I have questions. Okay, maybe I'll ask some questions of my own. Julian, is Myrtle working on other models apart from ASR that are going to take advantage of Acronic's FPGAs?
We're looking at the whole conversational pipeline. I mean, Bill is probably a better place to answer this one.
Yeah, so right now we're looking at Llama 2, which is an open source generative AI transformer model. Probably I would argue still one of the best ones today out there in the open source market. But as Julian said earlier, like, they change constantly, especially when you start saying the word, generative AI. I've never seen, it's like the social media blitz, from years ago. It's every 6 months, it's a completely exponential improvement. We'll call it an improvement, but certainly next step. So that's an area that I think in that generative AI pipeline, would be the next logical step, because typically when people do those large transformer models for generative AI, they tend to do them at scale. And that's, again, expensive and it's time consuming. So what we think is, again, I think it's like a 5 or 6x improvement on at scale, generative AI. So when you start getting to especially over 8 FPGA cards connected together compared to 8 GPU cards, the performance goes up, 1, 2, 3, 4, 5, 6x as you scale up to 32, for example. With the latency continuing to go down. So that the other piece is that the latency is significantly, it's probably a 5x reduction in latency. Even at scale, it continues to go down where a GPU is going to tend to plateau. So that's the area I think that we're looking at next. And then, of course, the back end of that pipeline, the text to speech, which could be much simpler from the perspective of a lot of people just need the one voice in and get one voice out. But we're certain, if there are people even listening to this who are interested in the text to speech or the generative AI, we would definitely want to know, so we can kind of position, do we really need to do that final text to speech piece, or is it kind of already covered by how people are doing the voice synthesis today?
Bill, I'm curious now that you've said Llama 2. What version of Llama 2 are you going to run? Like, how big is too big for an FPGA?
So we're pretty sure, and well, I'll speak for this again, Julian, but correct me or change it. I think right now we're going to do, we think the 13 billion parameter model should definitely fit in an FPGA. So 7 billion for sure, and possibly the 13 billion we need to try. I think 70 billion is going to be a scaled solution. To do the 70 billion will require multiple FPGAs. And Julian,
that's correct. 7 billion will definitely fit. A 13, which I guess we're not, I think, intending to do in the first instance, could fit at some particular precision, but yeah, 7 billion would be the single card. Yeah.
Oh, very cool. Okay, if there are no more questions from the audience, last call for questions. If you have a question for our 2 experts on ASR, AI for ASR, here we go.
Yeah.
Andrew, thanks for watching, Andrew. Any plans for HBM SKUs for Acronics?
So I would say no. Certainly not in the initial schedule of roadmap of products. For a couple of reasons. One, with our GDDR6, it's pretty competitive, I think, with the bandwidth of HBM, but also the lifespan of HBM not being overly long, where we can get GDDR6. I think GDR memory tends to have like a 10-year lifespan. So GDDR6 moves to GDDR7 and so on. I think we're getting the bandwidth we need out of that memory for the workloads we're trying to run. HBM is between cost and availability, longevity. Initial plans are not to try to pursue HBM in the short, next cycle of products.
Okay.
Could change if they change if some of those things change, but
who knows what will happen? But that's interesting that you're not considering it right now. Okay, Bill, if people are interested in finding out more depth on any of the things that we talked about today, how can people go ahead and get some more information?
Yeah, definitely. So I know that we've been flashing up some links here. We've got the demo that you could schedule if you want to see. There's our website that also was shown earlier too, that you can go and learn more. But basically, just reach out to us. We will facilitate the conversation with you, get you started. See the demo, and ideally the next step would be, well, I want to try it. So, then we could get Myrtle to give you the repository, and you could do your training on your own data set and on the CPU, and then move it over to the FPGA. But usually, once you do that, it requires some software, a little bit of a software layer now to interface to our stuff. But all of that stuff is possible today. We can start talking to you, and certainly by Q1, a lot of these things that extra things we've talked about will be available.
Yeah.
And if you don't want to retrain it, you can also try it. You can also get your hands on a box in the AVL and actually see those latency figures for yourself using those off-the-shelf English models that I mentioned before.
Got it. Thank you. Okay, well, if there are no more questions, thanks very much, everyone, for tuning in. Just one more thing I want to call out, which is that EE Times is hosting our own virtual conference on AI hardware. This is November 8th and 9th coming up. It's called AI Everywhere. We're going to focus on data center and server AI on the first day and embedded AI and TinyML on the second day. We have speakers so far from NVIDIA, Cadence, TenstorRent, STMicro, Synaptics, and tons of others. Completely free to attend. All you have to do is register. And to register, please go to aieverywhere.etimes.com. Thanks again to Achronic's Bill Jenkins and to Myrtle.ai's Julian Mack. And thank you, everybody, for watching. And thanks for the great questions. Have a good evening.
Thank you, everyone.